Hello and welcome to another math video. This one's going to cover Calculus, Chapter 4, Section 2. Here is the homework assignment. As usual, some of it here is on WebAssign. You don't have to pay attention to the numbers there. Out of the book on pencil and paper, we have these 6 problems. This section's got a lot in it. I'm probably going to split it into 2 videos. The first video here will probably have the first 3 examples. This is a big kind of deal here in Calc. We're sort of going to the other side of the calculus coin. We have spent a lot of time finding derivatives, instantaneous rates of change. Now we're going to look at area under a curve. Remember back at the start of the school year when I gave an overview of the course, I said we'd be taking the area under functions and chopping it up into rectangles and finding the area under that curve. And here's how it all begins. Just like with derivatives, we're going to explore this as our mathematical forefathers did and how they came to discover calculus here. So let's dive in. We got some bullet points here. We're going to use sigma notation to write and evaluate sums. There will be a quiz on the sigma notation. We will understand the concept of area. We will approximate the area of a plane region, a flat two-dimensional space, and we will find the area of a plane region using limits. If you do take Calc 3, you move out of planes and into three-dimensional calc. That's a lot of fun. So here we go. In the preceding section, we studied anti-differentiation. In this section, we'll look further into a problem introduced way back in 1.1, that of finding the area of a region in the plane. At first glance, these two ideas may seem unrelated, but you'll discover in a later section, 4.4, that they are closely related by an extremely important theorem called the fundamental theorem of calculus. This section begins by introducing a concise notation for summing things up. This notation is called sigma notation because it uses the Greek uppercase letter sigma written like this. It will not take too long where you will be sick of writing this symbol down in your homework and in your notes. So here we go. The sum of n terms, and they're calling them a sub 1, a sub 2, a sub 3, dot, 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 all the way to a sub n. That is the last term. And they write it like this. Here is my Greek letter sigma. They use different variables here for these summations. Usually down here it's I, j, or k. That is a terrible I. So here is I equal to, a lot of times these summations starts with 1. They don't have to start at 1 though. And then the end term will be up here on top. So we start at I, and this is also called the index. And we're going to sum up from the first number to the nth number, to the last one. And what are we going to be summing up? These terms a sub something, a sub I. And then they write it out up here, this summation from the first term to the nth term of a sub I, that is equal to a sub 1 plus a sub 2 plus a sub 3, dot, 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 all the way to the last term. I is the index of summation. You see either i's or j's or k's down there. A sub I is the ith term of that sum, and the upper and lower bounds are the n and the 1. So down here, this is your lower bound, and up here on top is the upper bound. And there's a sigma notation. Again, this was created just as a way to concisely show a summation of some amount of terms. Where would this be useful? Right here. So on the first one, it's just some examples, some concrete examples, at least the first 4 are. So here we're going to sum up from 1 to 6 all the numbers. So we would write this out as we're going to start at the first number 1, and we're going to add to 2 and 3 and 4 and 5 and 6, and that's equal to 21. Now, letter B, if we look at this, now we're going to start not at the first term, but at 0, and we're not going to go to 6, we're going to go to 5. And our function is not just the numbers, it's that number plus 1 more. So when we start at 0, 0 jumps in, 0 plus 1 is 1. Next number would be 1, 1 plus 1 is 2. and then 2, 2 plus 1 is 3, and 3 plus 1 is 4, and 4 plus 1 is 5, and 5 plus 1 is 6. And that's our last term because we stop at 5 and we add it to 1 and there's 1, or 6. Now notice that's exactly the same as we have above, so it's going to also equal 21. Now, I don't think we use it in this class, but in a higher level math course in college, you might see this little rule. If we add 1 here, we've added 1 into whatever we're working with, this I, we would subtract 1 from the top and the bottom. So if we subtract 1 from this 6, we get 5. If we subtract 1 from our index, we get 0. We subtract 1 from the upper and lower bounds, we do the opposite and add 1 here. So those will turn out to be the same sums. That is useful sometimes to make your computations a little easier. And now that I think about it, it might show up one time in this course, and I'll give you a heads up when that occurs to make that problem easier. What's next? Ooh, now we got some squared stuff. So j from number 3 to 7, we want to sum those up as squares. So our first term is going to be 3 squared, and then 4 squared, and then 5 squared, and 6 squared, and we get to 7 squared, and that's our last term, and we stop. Now, if you're curious, those do add up to 135. Okay. Letter D. Now we got some radicals in there. So we're going to start j as our index from 1 to 5, 1 over root j. So this is going to be 1 over the root of 1 plus 1 over root 2 plus 1 over root 3 plus 1 over root 4 plus 1 over root 5. And there it is. We could punch that in a calculator and get it as a decimal, but I didn't go that far, and neither does the textbook. Now those are real concrete ones. Here we're going to get more into the abstract part, because notice our upper bound now is just n, and in this one it's a little different. We have a 1 over n here. And then we've got our index k squared plus 1. And notice, since they did leave this as n, we could go out to infinity. So again, this is going to be a little more abstract. So we would start with 1. We're going to have 1 over n times quantity, 1 squared plus 1. And then our next term would be 1 over n times 2 squared plus 1. Plus, come down here, 1 over n, quantity 3 squared plus 1. And I'm going to stop there and give her the old dot, dot, dot to show there's more going on in there. And now let's get to the last term, 1 over n. And then remember our upper limit here is n, so that's what's going to hop in last. So that's going to be n squared plus 1. And again, that's our last term, so we're going to stop right there. All right, one more to go, and this is going to get a little more into the notation that we'll be seeing later. We're taking baby steps here. We're learning to walk before we run. So now here's a little function notation, f of x of some subscript times delta x. So, and we're going to go from 1 to n. So our first term is going to be f of x sub 1 times quantity delta x. Plus, next would be f of x sub 2 times delta x, plus, moving down here, f of x sub 3, that times delta x, dot, dot, dot. Here's our last term, our nth term, f of x sub n times delta x. And there it is, some examples of sigma notation. Now you notice I left example A up there, and we're going to come back and revisit this once we check out our formulas, because here this one's not bad. We could sum those up no problem, just count it up in your head. But what if that was a summation from 1 to 812? Of the numbers. That would be painstaking to do long way, but we're going to find a formula for that shortly. And here are the formulas. It says first, the properties of summation shown below can be derived using the associative and commutative properties of addition and the distributive property over addition and multiplication. In the first property, k is constant. These properties might seem familiar. We saw them with limits and derivatives. These properties here are just seeping all through calculus. If we have a summation of some constant k times a sub I, we can pull that constant out front, just like we did with constants in deriving and with limits. Here we have the summation of a sub I plus or minus b sub I. Sort of like we distribute, we could do just the summation of the first term, a sub I, and add or subtract, whatever necessary, the summation of b sub I. So we could split that into separate summations, just like we did with limits and derivatives. Now here are the summation formulas. In class we will have a quiz on these before the test, and then they will be printed on the test. Let's start with number 1, of course, summation from I equals 1 to n of c. Now notice this c is going to be a constant, like a 7 or a 20. If that's the case, whatever this upper limit is, n, we bring it down and just multiply. So that's going to be upper limit n times c. Let's go over here to number 2. The summation from 1 to n of I is n times n plus 1. And then you divide that by 2. Now we're going to go out of order here. Let's go down to number 4 right below. So we're going to go from the summation of I to the summation of I cubed, because look what you do. I'm going to take this n up here and square it. This n gets squared. This quantity n plus 1 also gets squared. Our denominator 2 gets squared, and now it's a 4. So to go from the summation of I to the summation of I cubed, you just square each term. Number 3 over here, I squared, is sort of the odd one. So I squared summation, it's kind of the same. We have the n times n plus 1 that we saw up here. Our denominator's now a 6, though, and we've got a new term, 2 times n plus 1 for I squared. If you are curious, you can see the proofs of those theorems in Appendix A in the book. Now, let's go back to example 1, because I did not erase 1a, because we can use this formula. It fits perfect. We're going from 1 to some number of our summation of I. So, instead of doing this, we could use our formula, n times n plus 1 over 2. So our upper limit here, our upper bound is n, so that's going to be a 6 times that next number up, n plus 1 is going to be 7, and we divide that by 2. 6 times 7 is 42. If you cut that in half, you get 21. Again, this is much more impressive on very large numbers here. Sweet. Now, if you're in my class, you know I'm a history or a math history nerd. Where did this idea come from? Let's take a little step back in history. Great mathematician Carl Gauss back in the 1800s. The teacher one day was not very motivated to teach, so he gave the kids some busy work, and he said, okay, class, I want you to add up all the numbers from 1 to 100. He figured, okay, that'll keep them busy for a while. Gauss returned with the correct answer in only a few moments. The teacher looked on in astounded silence because he got the answer right. Here's what Gauss did. Okay, he thought, okay, if I'm going to sum up the numbers from 1 to 100, 1 plus 2 plus 3, to 100, what if I put the same numbers underneath in reverse order? So now we're going 1, 2, 3, 98, 99, 100. Well, if you add the columns, each column is going to be 101. So, and you've got that sort of double of what you wanted. So if you multiply those and divide by 2, you get 5050. This is generalized in our theorem for 2. The summation of all the numbers from 1 to 100 is 100 times the next number, cut it in half, 5050. I'm still trying to track down exactly how old Gauss was when he did that. You know, it'd be pretty good if he was in high school, even better if he was in middle or elementary. Okay. Example 2. Let's sort of apply this here. It says, evaluate from the first number to the nth number, I plus 1, over n squared for these different n values, 10, 100, 1,000, 10,000. Okay, so here's how we use these n formulas. I'm just going to copy the exact same thing we have here. We have our summation from I equal, excuse me, my eyes are going to be terrible. I can't hardly do dots with this pad I'm working with, to n of I plus 1 over n squared. So what we want to do is after the summation, we only want i's and numbers. We have an n squared, but we can pull that out front. So this n squared in the denominator, I'm going to drag it out in front of the summation symbol. So when it's out in front of the summation, it is now going to be 1 over n squared. And we're going from I equals 1 to n. So now what we have here is just I plus 1. So just i's and numbers, and that's exactly what we're going for. So next step, we're going to apply one of those properties of summations, and we're going to distribute the summation to both of these terms. Now the way I'm going to do it, I'm going to keep this 1 over n squared. I'm going to put it outside a set of brackets because this 1 over n squared does apply to everything going on over here. Now let's distribute our summation. So we're going to have the summation of I plus the summation of 1. And well, from I equals 1 to n, I equals 1 to n. That's supposed to be an n. There we go. So now we've got it set up so it looks a lot like the formula sheet. We have a summation of I, we have a summation of a constant. So at this point, we can apply the formulas. I still have my 1 over n squared outside my brackets. So now here, I'm going to circle it in red. We have from 1 to n, the summation of I. All of this is going to disappear and be replaced with the formula n times n plus 1 over 2. Plus, we have another summation, the summation from 1 to n of just 1. Now remember, this is where we multiply the number up top, our upper bound, and this constant. So when I multiply those, I get 1 times n, or n. And I'm going to close off my brackets. Okay, now it's algebra time. I warned you in pre-calc, a lot of calculus is algebra, and here is just another great example of that. Now, to get a common denominator here, I'm going to make this a 2n over 2. So, now I'm going to distribute and combine like terms. I've got n times n, that's an n squared. N times 1 is n, and I'm going to add that to this 2n, so now I've got 3 of them, 3 n's, and that's over the common denominator 2. And I've still got lurking out here 1 over n squared. So I can get rid of these now. Okay, time to simplify with a little more algebra. Now we could think about it this way, we could put a set of parentheses here and factor an n out and then cancel it with this n squared in the denominator. But I'm going to be a little more risky and do it like this. We're going to reduce this n by a power of 1. That's going to reduce this by a power of 1. And this will also reduce by a power of 1 down to n to the 0. So it disappears. Okay, so what are we left with? Our numerator is just n plus 3. Our denominator is 2n. This is our shortcut formula, so to speak. So we want to, if I drag this down here a little bit, we want to do the summation of that. Now, this looks different, but it'll give us the same answer, the same output. So now, let me move this over here. We can plug in some values and fill in the box. So what if we were going to sum up from 1 to 10 of this number? Well, we just plug the 10 in, and we're going to get 10 plus 3 is 13, over 2 times 10 is 20, 13 twentieths, or 0.65. Let's plug in a bigger number, n is 100. So that's going to be 100 plus 3 is 103. Over 2 times 100 is 200. As a decimal, that will be 0.5150, 5150. What if we wanted to sum up 1,000 numbers? Well, that's going to be 1,003 over 2,000. As a decimal point, 50150. All right. What about a bigger number? 10,000. That's going to be 10,003 divided by 20 grand. That is 0.50015. Okay. Now this is not in the book, but let's think back to limits. Remember all the good times with limits? What about the limit as n goes to infinity? Remember, that's what I call in class the power struggle between the numerator and denominator. Which is more powerful? It's a tie, n to the first. So what is the limit? We make a fraction out of the leading coefficients, 1/2. What's 1/2 as a decimal? 0.5. That sure looks like where we were headed down in the table. 0.6, 0.51, 0.501, 0.5001. The farther out we go, the closer we're going to get to 0.5. And what does this say? Oh, yeah, there it is. In the table, blah, 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 no, treat it as a limit. And here they sort of broke it into separate terms. Now you don't have to do that. Remember to look for that power struggle. Okay, now we start talking area. We're going to need this summation stuff to come up with our areas under curves. But first, let's do a little basic talk about area. In Euclidean geometry, the simplest type of plane region is a rectangle. Although people often say that the formula for the area of a rectangle is base times height, it's actually more proper to say that is the definition of the area of a rectangle. From this definition, we can develop formulas for the area of many other plane regions. For example, to determine the area of a triangle, we can form a rectangle whose area is twice that of a triangle as shown in the figure. Once we know how to find the area of a triangle, we can determine the area of any polygon by subdividing that region into triangular regions. So if you got a parallelogram, just do a diagonal, you got two triangles. Hexagon, do your sort of diameters there, you've got triangles. Any odd-shaped polygon, if you pick one of the vertices and then connect it to the other vertices, you will have some number of triangles. And we can figure out the area of those individual triangles and sum them all together. Ooh, what's this? Archimedes, my all-time favorite mathematician ever, way back in the hundreds BC, he used the method of exhaustion to derive formulas for the areas of ellipses and parabolic segments and sectors of a spiral. He is considered to have been the greatest applied mathematician of antiquity. Calculus was discovered in the 1700s. Archimedes actually had sort of peeks into little tiny parts of calculus, but he did it by an exhaustion method. What he did was light years ahead of his time. Fantastic mathematician, terrible body odor. Finding the area of regions of other polynomials is more difficult. The ancient Greeks were able to determine formulas for the areas of general regions, principally those bounded by the conics, by this exhaustion method. The clearest description of this method was given by Archimedes. Essentially, the method is a limiting process in which the area you want is squeezed between two polygons, one inscribed in the region, one circumscribed about the region. For instance, down in the picture below, the area of a circular region is approximated by an n-sided inscribed polygon and an n-scribed circumscribed polygon. For each value of n, the area of the inscribed is less than that of the circle, and the area of the circumscribed is greater than that of the circle. Moreover, as we slice it into more and more chunks, more and more sides to our polygon, the area of both polygons becomes better and better for the approximations in the area of a circle. So what Archimedes did is he was trying to figure out a definition of pi, or the area of a circle. Take a circle, put around it here, we've got a six-sided polygon. So if we find the area of that, it would be an overestimate of the area of the circle. We could also put the same number of sided polygon inside the circle, and we could find the area of that polygon. And then the area of the circle would be somewhere in between. The bigger polygon would be an overestimate, the red polygon would be an underestimate, and then the truth would be somewhere in between. If it was good for a 6-sided polygon, how about a 12-sided polygon? Notice now the error, the over and under estimate, has gotten much, much smaller. And you could do this out to, I think Archimedes might have taken it out to a 100-sided polygon and got a very, very good idea of the area of a circle and a very good estimate of pi. Thank you, Archimedes. Here we go. This is going to be a big example. This will probably be the last one in this video. I believe I left you one full page in your notes to do example 3, the left endpoints. And then there might be on another page the right endpoints. Or that might be, I might be forgetting, that might be a later example. Because I think on this one we're going to do the one estimate using the formulas and a bunch of algebra. And then the other estimate, the overestimate, we'll do that with a calculator in class. I'll show you how to do this on the TI-89s. So what I'm going to do here, I'm just going to move this down out of the way. Recall from 1.1, way back in chapter 1, the origins of calculus are connected to two classic problems, the tangent line problem and the area problem. Example 3 here begins the investigation of the area problem. So let me make this a little bigger. Use the 5 rectangles in the figure, and we're going to make the rectangles ourselves, to find 2 approximations for the area of the region lying between the graph of, here's our upper bound, our negative x squared plus 5, that is this downward opening parabola, y-intercept of 5. We want to find the area under that, and bounded by the x-axis between 0 and 2. And let me make a new slide here so I can put this graph on it and make it nice and big so I can draw all over it. Okay, now it says here, let me go back to the setup. We're going to go from 0 to 2. So here is x is 0. This out here is going to be x is 2. So that's 1, 2, 3, 4, 5. We've got 5 rectangles that we're going to bust this up into. And let me say here for the first one, for letter A, we're going to do the left endpoints. Left endpoints. That's supposed to be an I, left endpoints. Okay, so, and where it says here, use 5 rectangles. So over here, if I go back to the picture, we are here, you know this, I'm going to label this rectangle 1, rectangle 2, rectangle 3, rectangle 4, rectangle 5. If we're doing a left-hand sum, rectangle 1's left end point is at 0. And if I go up until I hit the curve, back up, scratch out that left, we're going to do right endpoints. My bad, right endpoints. The right endpoints, most of the time, are a little bit easier. Those are the ones we'll do longhand with the algebra. The left endpoints we'll do with the calculator. Okay, so scratch the right end, or the left endpoints. Let me throw that in the garbage. We're going to do the right endpoints. So here again is rectangle 1. Its right endpoint would be here. And we're going to take that up until we hit the curve, and then we're going to break to the left to make a rectangle using the right endpoint. Rectangle 2's right endpoint is here, and I'm going to take that up until I hit the curve, and then I'm going to break to the left to make rectangle 2. Rectangle 3's right endpoint is here. We're going to take that up to the curve and break left. There's our third rectangle. Rectangle 4's right endpoint is here. Up to the curve, break left. Rectangle 5, right endpoint here, till we hit the curve, break left. Now we're doing right-hand endpoints, and our function is decreasing, so this is going to be an underestimate. When we get our answer, notice we are missing area. We are not counting it. It is under the curve, but it is not in our rectangles. So our rectangles will be an underestimate. We will do an overestimate with the left endpoints, and the truth will be somewhere in between. So now here comes the more difficult part of this problem. We need a formula that when we put in the rectangle number for I, it's going to take us to the right endpoint. Ooh, but first let's figure out what these are. We've got 5 rectangles. We're going out to 2. So here we're going to, let's do this, b minus a over n. A and b are our upper and lower bounds, and n is the number of rectangles that we want. So here, our right endpoint is 2. Our left endpoint is 0, and we're going to divide that by n, and we want 5 rectangles. So it says here, this is basically the width of the base of our rectangles, how wide our rectangles are on the base, and it's 2/5. So this right endpoint here is going to be 2/5. Next one will be 4/5, and then 6/5, and then 8/5, and then 10/5 turns into the 2. So there are the right endpoints. Those are what are going to go into the function to determine the height of the rectangle. So again, we need a formula. When we put 1 in for I, we get the right endpoint 2/5. When we put 2 in for I, we get the right endpoint 4/5. When we put 3 in for I, we get the right endpoint 6/5. And the reason we're doing this, the right endpoints longhand, is, this is the easier way to go usually. The first thing I'm going to check is just take that rectangle base, 2/5, and multiply it by I. So if I put in I as 1, I get 1 times 2/5, or 2/5. If I put 2 in for I, 2/5 times 2 would be 4/5. If 3 goes in for I, 2/5 times 3 is 6/5. So this is our right endpoint formula. I'm going to come back here. Right endpoints, our formula is going to be 2/5 times I. Okay, our rectangle width, my spelling is terrible, width of rectangles, that is our delta x, or our dx. Remember, those are interchangeable. What is the width of each of our rectangles base? 2/5. We can see that nice and graphically here. 2/5 is the base of each. That's nice and consistent. It's the heights of the rectangle that are changing. So our dx, or our delta x, is 2/5. So what determines the height of each of our rectangles? Well, remember, we put in an x value, and now we're going up until we hit the curve. So this function determines the height of our rectangles. Oops, wrong way. So the height is going to be f of the right endpoint. We take the right endpoint, we put it in a function, that gives us the height of the rectangle. So, yeah, I guess I can erase this. Do that. So, to put this into summation notation, we're going to sum from I equals the first rectangle to the 5th rectangle, f of our endpoints, 2/5 I, times 2/5. Now think about this in geometric terms. An area of a rectangle is base times height. The 2/5 is the base of the rectangle. The function determines the height. F of the endpoint is going to give us the height. So here is base times height. Now, this is where some students run into confusion. We are going to make the jump actually into the function. This is function notation, f of. This is our function up here. So we're going to make that jump into the function. So we're going to have our summation from I equals 1 to 5. Now our function, I'm going to put a set of brackets here, is negative x squared plus 5, or negative x squared plus 5. So this is going to be the height of the rectangles. And let me switch to red again, because we've still got the base, and now that's just that 2/5 is our base. So we're going from function notation to using the function. Now notice I left the variable out there because we're not going to square x anymore. We're going to square 2/5 I, our endpoint formula. Okay. Now it's time for more algebra. Oops, let me get that out of there. So let me go back to black ink here. We've still got our summation notation. Pardon me while I don't do my upper and lower bounds there. So here the negative is outside the parenthesis, and we're going to square everything in there. When we square 2/5, we get 4 over 25. And then when we square the I, we get I squared. Oops, no, that's not -1. Don't think imaginary numbers. So that's our 25th I squared. And remember, it is negative. I guess I really didn't need those parentheses. And then we have our plus 5. Ooh, now what I should have done in this step, this base, the 2/5, that's just a constant. We can sort of factor that out and move it out here in front of the summation. So I'm just going to slide this over. I can close these brackets because now the 2/5 is out front. That's one of our properties of summations. We can pull constants out here in front. Now we are going to use another one of those properties. We're going to kind of distribute that summation. Now we could leave the 2/5 out here and do the distribution of the summation in more brackets, or in this case, I'm going to distribute the 2/5 with the summation. So 2/5, I'm going to switch to red ink for the first one. 2/5 summation is going to go to the first one, so we're going to have 2/5. The summation of negative 4/25 I squared plus 2/5 the summation of 5. Okay. Again, pardon me for not putting the I equals 1 to n in there. Again, working with this pad, doing small lettering, it's sometimes a pain. So put it up here. Okay. It is time for more simplification. So here on this one, we can factor the negative 4/25 out with that 2/5. So that is going to be numerator times numerator, -8 over 5 times 25, 125. And now we have, let me switch back to red ink, the summation of just I squared. We have a formula to take care of that. Plus, now here, remember, this is from I equals 1 to n. Well, let's just leave this as is for now. 2/5 the summation of 5. Now, I am going to put my back in there. I equals 1 to 5. I equals 1 to 5. All right. We are now ready to use those brand new summation formulas. So, of course, this fraction is going to remain intact, -8 over 125. But I'm going to block off here in blue. We have this summation. So that is, remember, n times n plus 1. Now that is, well, I guess I'll just write it out here. N times n plus 1. Well, remember that n is a 5. So that's going to be n times n plus 1, 6, times 2n plus 1 is 11. And that's divided by 6. Okay. Plus, next term here, we have 2/5. And remember the summation here, when that's just a constant, we multiply these together. So that's going to be 5 times 5 is 25. And I'm going to put it over 1 like so. All right, move this up. To make our computations a little simpler, we can, since we wrote it like this, cancel those 6's. So that's going to be -8 1/25 times 55. Plus, we can cancel here on the diagonal. That's going to be 2 times 5, or 10. And we could punch that in our calculator. Or if you want to keep it in the form of a fraction, 1/62/25 which is approximately 6.48. 6.48. Now again, this is an underestimate. If I go back to my picture, we're trying to find the area under this curve. We've used right-hand endpoints on a decreasing function, so we are missing some area. So keep in mind this is an underestimate. The true area under that curve is going to be more than that. Okay, now go here. Oops. Let me drag this problem back down. So we need two approximations. Our other approximation is going to be the left endpoints. So here again, we are going to go from 0 to 2 to 2, dividing our rectangles, by base 2/5. So that's still going to be 2/5 and 4/5 and 6/5 and 8/5 and 10/5 is 2. But now this time we're going to do the left endpoints. So when we do our first rectangle, number 1, our left endpoint is the y-axis. We're going to go up until we hit the curve, and then we're going to break to the right and then go back down to create our rectangle. Ooh, and I should have just done it like that. Rectangle 2, left endpoint will be the 2/5, and we're going to take that up to the curve and break right. Oops. Up and break to the right. Rectangle 3's left endpoint is 4/5, and we're going to go up until we hit the curve and break right. Rectangle 4's left endpoint is 6/5. We're going to go up till we hit the curve and break over. So notice here now, all of these are extending beyond the curve. So this, we're counting area that's not under the curve. So in this case, we will have an overestimate. It's going to definitely be bigger than the 6.48 we found in the first estimate. Ooh, I shouldn't have erased that. Now here, we need to find the left endpoint formula. Now when we found the right endpoints, that was pretty easy. It was just 2/5 times whatever rectangle we were working with. Rectangle 1, 2/5 times 1 took us to here. 2 times 2/5 took us to the right endpoint. But now we need to plug in I as 1 and get back to the left endpoint. So let's think about this logically. If 2/5 times I, or 1, takes us to 2/5, how would we get from 2/5 back to 0? How about by subtracting 2/5? So let's even try that. Let's say we put in rectangle 4. If I put 4 in for I, that's going to be 2 times 4 is 8, 8/5. But then I'm going to subtract 2/5. 8/5 minus 2/5 takes us to 6/5. And that is the left endpoint for rectangle 4. So we found our left endpoint here. That'll get us to the left endpoint of any of those rectangles. And we could, to make sometimes our computations easier, a common denominator 5, and we could factor a 2 out, leaving I minus 1. So there's a little formula. If we put in the rectangle number for I, it will take us to the left endpoint. Now, let's set this up algebraically, but then I will show you how to solve this on the TI-89. So what we would have here, and I guess you have this in your notes, I'm going to erase it from here. We would have the summation from I equals the first rectangle to the 5th. Now we're going to do f of 2 times quantity I minus 1 all over 5 times 2/5. Remember, in the big scheme of things, f of our function is the height of the rectangle, because we're going to go up until we hit the curve, so the function determines the height. The base is a constant. All our rectangles' bases are 2/5. Now, if we were going to do this algebraically and make a jump into the function, we would go from I equals 1 to 5. We would have negative some quantity squared plus 5. That is our jump into the function. And then out here we would have our base 2/5. But now, before where we just put 2/5 I in here, we're going to have the much more complicated 2 times quantity I minus 1 all over 5 squared. So here, if we were to take this algebraically farther, we would have to distribute the 2, FOIL that out, distribute these summations. It's going to turn into an algebraic mess fairly quickly. But another aspect to this class is getting good with the TI-89 calculators. Now write this down in your notes. We'll probably have time to work on this in class. There is a summation drop-down menu, and what we're going to do is type in there our 2/5, and then we're going to bring up the summation symbol. Now be very mindful of these parentheses, negative, another parenthesis, followed by another parenthesis, and then we'll put in there our 2x minus 2, and we will close the red parenthesis, but then we're going to divide by 5. I guess I'll just use the regular old school. Divide by 5, close the blue parenthesis, and then close the black parenthesis, up caret squared. That's our squared quantity. And I'm going to sneak down here, and we're going to have plus 5, and then comma. Now we need to tell what variable we're working with, even though there's only one variable there. The calculator will only do what you tell it. So give it a comma x, comma 1, that's our lower bound, comma 5 is our upper bound for 1 to 5 rectangles. Close off, close, I guess I had white ink there, close our other set of parentheses. So I got those. Yeah, we closed off, we started with a summation of a parenthesis. That is our closing parenthesis there. So let me double check my parenthesis here. Back up. We got to get this one out of here. Yeah, it's a good thing I color coded it because the red ones are here. The blue ones are here. That's our quantity squared. And then our plus 5 is outside that. The black parentheses are closing off the summation. There it is. Now, I'm going to spoil the surprise. You punch that in your TI-89. You're going to get 202 over 25, which is approximately 8.08. Now, keep in mind, again, this is our over estimate. So when we're trying to find the area under that curve, our under was 6.48, under. 8.08 was our overestimate. So somewhere in between there is the actual true value underneath that curve. Whew, that's a big example. That's a big, now what do I see down here? Oh, that's just the picture we were using. That's the one we did before. Okay, this is a good spot to stop this video. I'm getting a little tired. I will make another video 4-2 day 2 or video 2 to wipe out the rest of these examples. I'll talk to you then.